Time to get into Chapter 2, Lesson 2. In Chapter 2, Lesson 2, we're going to deal with different types of friction and what friction actually is. We're also going to talk about gravity and then compare the idea between weight and mass. So let's start with friction. So when I have two objects that are going to slide or rub or glide over one another, it's going to cause friction. Each object is going to have force, either a push or a pull, on that object. So our definition that we should write down in our notes or mark in our book is the force of two objects that are exerted on each other. Now, exerted just means to be pushed against or pulled against or rubbing against one another. For example, we've all done this little science experiment proving that friction exists, right? So when we rub our hands back and forth, we're going to create heat. The faster I rub my hands back and forth, or the harder I push when I'm rubbing my hands back and forth, the greater the heat is going to be. Why does that happen? Well, we have these little itty bitty ridges all over our fingers, right? Called fingerprints. So it's all of those ridges, those bumps that go up and down, that as they rub on each other, because it is not a completely smooth surface, then we're able to intensify the amount of heat that we create by simply rubbing our hands together. When I talk about the idea of friction, then if I need more friction or want more friction, then once again, I rub my hands faster, I push my hands harder together, or I do both. And when I do both, then I get a much greater intensity in that heat that I am creating. So when we look at the idea of those ridges, it's the ridges that are coming into contact or rubbing against each other that's creating the friction. And the friction is going to create heat. So when we talk about friction, we want to talk about two different things that are going to affect friction. Could increase or could decrease. So the first thing that we look at is the type of surface. We could have a very smooth surface, we could have a very rough surface, and friction is going to be affected by the type of surface that we have. For example, I could have a smooth piece of wood, or I could have a very rough piece of sandpaper. I could rub my hand on both of those, right? But we should know by now in life experiences that when I rub my hand along smooth wood, that it is going to create friction, but it takes me usually rubbing my hand faster and or pushing down harder for me to get more friction, right? To increase that heat. Whereas with rough sandpaper, not so much, right? It doesn't take hardly any pressure or speed to rub my hand across, and it's going to take that top layer of skin right off. So the idea is that as I'm rubbing on specific surfaces, the smoother it is, the least amount of friction is going to be caused, or the least amount of heat I'm going to create. But if it's a rougher surface, it starts out already with a greater amount of friction. Therefore, if I rub it at the same speed, I'm going to get a lot more heat from it. The other option then is, or the other item that affects friction is the idea of the force that's exerted upon it, right? So if it has a greater mass, then it's going to be more difficult for it to move. For example, right, if we have this girl in this chair and I need to move her, it's going to take some effort, right? But the legs on the carpet is going to create friction. I'll still be able to do it. I'll still be able to overpower that friction because her force, her mass is not very big. Versus somebody that is about your size sitting in the same chair. They're going to have more force, they're going to have more gravitational pull. Therefore, it's going to take more effort for me to get the friction to break and then to push them across the carpet. Whereas if I have a really big person sitting in the same size chair, it may be extremely difficult to get them to move, or it may be impossible. So when we talk about the idea in our book, then they go to the idea of football. So if you don't know what football is, so this is a tackling dummy. This is one of the items that they will use for defensive and offensive linemen to practice blocking and pushing their opponent out of the way. So the black thing in the back is a large metal sled, and usually a coach will stand on it. Your book gives you three different surfaces that we could push that sled across. And if you had to move that sled with the coach standing on the back of it, and you had to attack it and push it, then we have three different options that you could choose from, right? Hopefully it would make sense, which is going to be the easiest versus the hardest, and therefore the middle one should be pretty quick. But the easiest should be the ice, because the ice is going to be compacted water, is going to be extremely smooth, and if you don't realize that, next winter find some ice and try walking on it. It becomes quite difficult. Where the grass or the astroturf, depending on which that is, it's going to flatten out as you're pushing across. It's going to be more difficult than the ice, but not nearly as difficult as the track. So some of you run track right now as a sport. You know that our track is pretty rough. Most tracks are, right? So it's very coarse when it comes to the surface, and therefore it's going to be more difficult to push that sled along it. It's going to have increased friction. If I wanted to make it difficult, let's say we're going to do it on the football field. If I want to make it more difficult for my linemen as they're practicing, then I would add another coach and another coach and another coach on the back of that sled and continue to make them try to push it. Right? So the more force is going to be more difficult. The more coarse the surface, the more difficult it's going to be. Right? So when we talk about friction, we are talking about a force that is always pushing in the opposite direction. Right? It's a force that we have to overcome in order to get motion to happen. Motion is driving that sled forward coming from the football player. Friction is happening from all three of those surfaces, though smaller amount in the ice, a much greater amount on the track. But we have to overcome it. So let's say Junior is going to help us move into our brand new house, right? He has a large box that we need to put over to the left there by the fireplace. He brings it into the kitchen and dining area where there's laminate flooring, and it's pretty smooth to move the giant box. But once he gets to the carpet, it takes a lot more force to overcome the friction that the bottom of the box and the carpet itself is making. Therefore, the rougher it is, then the more difficult. So therefore, with friction, we've got four different types that we're going to learn. The first one should be pretty easy because it says its name and gives you the definition all at the same time. So we have sliding friction, and our book tells us, we should be marking it, that when two objects are sliding over one another, then we have sliding friction. Right? Some things we know are going to be more coarse when it comes to their surface than the other, therefore the friction can change. But it is the idea of one object sliding over another. The object that's being slid over is what's going to be pushing against the other one. So for example, Junior pushing a box across the carpet, the motion is the box that's moving. The friction is what's happening when the carpet is trying to slow you down. So we have motion, we have friction. It's kind of like if you have a stubborn dog like mine and he just decides he doesn't want to go anywhere, right? He's going to put his feet into the ground, and there are times I just have to drag him, right? His rear end going across the ground is creating friction because the ground is saying, yep, nope, we don't want him to move, and I'm trying to pull him, right? So the motion is me pulling, and he is sliding his rear end along the ground because he's a big stubborn dog. The idea of the penguin that they give you in the book is the idea that it's going to slide down the ice. Now it tells us that as it's sliding down the ice and the motion is carrying the penguin, friction is happening with the ice, that if it wasn't for that friction, we might have a problem, right? Because the penguin would just bang and hit the wall. Right? Friction helps the penguin slow down before it gets hurt. It's the same idea with you and your bicycle. So if you go out riding your bike, hopefully you know what these things are. They're called brakes. They're good to have on a bicycle. If not, your feet get really hot trying to stop your bike, right? So you have those brake pads usually operated by a handle grip, or if it's just a regular bicycle without hand brakes, then you just push your pedals backwards. But what ends up happening is those plastic or rubber pads, excuse me, squeeze in on the tire. They're going to heat up because the rubber is pushing against the metal rim of the tire, and it's going to gradually slow you down, right? You don't want to squeeze your brakes all of a sudden if you're going 10 miles an hour because you might flip your bicycle over, right? But you want to gradually slow down. If you would slow down after riding super fast and then get off and feel that metal rim of your tire, you're going to find out that it's hot because friction is going to create heat. So we have sliding friction where we slide. We also have what's called static friction. Now, don't get confused between static friction and static electricity. So static electricity is the exchange of positive and negative electrons attracting one another where you get a snap, right? So if we get into that, that'll be later in our book. When we're talking about static friction, it's where there is a lack of motion, right? So the book tells us that static friction is a force that's keeping something from moving. For example, when I have a large couch and you're trying to push it across the carpet, you just may not be strong enough to move it across the carpet. It may be a really large, heavy couch, right? It's just sitting there waiting to be moved, right? You have to break that static friction in order for the object to move. It would be like all these individuals trying to move this elephant. If that elephant is sitting down, it's going to be very difficult to get him to move, right? Static friction. We can push and push and push, but we don't have enough force in order to break the friction that's keeping the elephant sitting down. If you went hiking and you saw this big rock, you may think it fun trying to roll the rock down the side of the hill, but you would have a very difficult time because no matter how much force you apply, you're not strong enough to break the static friction that's keeping that rock sitting on the cliff. All right, so sliding slides, static stays, and fluid friction. So when we talk about fluid friction, we have to think about fluids, but not just water, which is what often happens, right? So when we talk about fluids in science, there's a large variety of them. But as something goes through a fluid, like swimming, then that's going to be fluid friction. We're trying to propel ourselves forward with motion, and the water is causing friction on our body. It's why most swimmers, if they get into competitive swimming, especially for the guys, they'll shave all their legs and their arms to reduce the amount of friction that's happening in the fluid or in the water. When I talk about an airplane, though, it also has fluid friction because the air is going against the plane. The motion propels the plane forward, but the air is holding it back. That's why if you have a flight and you go from east to west and then west to east, same direction, you might have a longer trip going one way because storms are happening and blowing against the airplane. You can prove the exact same thing with air anytime you ride in the car with your hand out the window and you play with the air. I'm sure all of you have done it. I still keep my hand out in the air and do it, right? But you're playing with fluid friction. That air is pushing against your hand. If you do the image that's on the left, then your hand just kind of glides through the air. You open your palm, fingers open, then it's a little bit more, tense to push against that air. But once you close your hand going against the wind, your arm's going to fly back, right? That's fluid friction. It's trying to prevent something from going forward. When we walk, we also have fluid friction, even though we don't think about it. Our motion is propelling us forward, but the ground is and the air is trying to keep us from moving. If you go outside on a very windy day and you're walking towards the wind, there are sometimes it becomes very difficult to walk forward compared to a regular day where there isn't any wind. But another place that we apply fluid friction is when we have things like cake batter, right? It's not really a liquid, it's not really a solid, But as we're mixing it, we have this fluid friction, and as the components bind together and become thicker, it becomes more difficult to break those bonds of fluid friction. The motion is us constantly stirring, where the liquid or the cake batter or whatever it is we're mixing up kind of slows us down. So sliding slides, static stays, and fluid flows through a liquid or an air. The last one that we have then is a rolling friction, and rolling friction tells you exactly what it's doing. It's going to roll, right? So when one object rolls across the surface of another object, we have rolling friction. Those of you that are in bowling, then you know that your bowling ball, your goal is to get it to go down the alleyway and knock over the pins. As it's rolling, it has friction that it is creating. The motion carries it forward as it rolls, and the bowling alley, the wood panels, is creating friction to slow it down. Vehicles are the exact same way. Doesn't matter if it's a car, truck, or a bicycle. As those tires are going along the road, the motion is propelling the vehicle forward, but the road is providing friction to keep you from rolling freely. The idea of the Egyptians building the pyramids, the concept is that they used rocks to help roll these large stones as they built the pyramids, right? But that rolling friction, we had a great mass of stone that was being pushed up. It kept it to be a difficult task, if you will, to be able to move those up. But the rolling of the logs with the motion of the stones going up, shifting gears then into the last concept of this section, lesson 2, is the idea of Mr. Sir Isaac Newton. So Newton was a great mathematician, physicist, logic thinker, and he discovered or proclaimed, if you will, the law of gravity. Right? Some people sum it up as basically what goes up is going to come down. Right? Now he didn't apply that to the moon because he didn't know out in space you don't have gravity or you have very intense gravity depending on what planetary object that you are on. But here on Earth, it's been true that if I throw something up in the air, it's going to come back down. So when I look at gravity, we need to know what we're talking about. And we have mentioned this before, so hopefully it's not a new concept, right? But gravity is simply the idea that things are pulled together, right? There's going to be a center force, and it's going to pull those objects towards it. So when I look at the Earth, then I know doesn't matter if I'm standing at the North Pole, South Pole, or if I'm in Europe compared to North America, South America. If I throw something up in the air, it's going to fall down because the center of our gravity for our planet is the center of the Earth. It's our core, right? So as we spin, everything's being pulled to the center of the Earth. But we have to understand that there is a difference between the idea of mass and weight. So back in Unit 6 of your math book, we had a whole conversions lesson, right? We dealt with masses and we dealt with weights when it came to objects. So when I'm talking about mass, I'm talking about the amount of space that an object takes up. You and I, we take up a certain amount of mass. I take up a little bit more mass than you all do, right? A little bit more space than you, but it's the idea of how much it will fill up. Where weight is measuring the gravitational pull on an object. If I go to the top of a mountain where there's less gravitational pull, then I'm going to weigh less than if I go to the deepest parts of the earth, not inside the ocean, but like on land, then I'm going to weigh more because I'm closer to the pull of gravity. So mass is going to measure size and the amount of space and molecules that are inside of an object compared to weight is measuring that mass with the gravitational pull attached to it. So when we talk about mass and weight, then our SI measurement is going to be grams or kilograms, where when we talk about weight, then you and I talk about pounds and ounces. So when we talk about universal gravity, then, this is an introduction for 7th grade, then that's the idea that everything in our universe pulls towards one another, right? There's a constant battle. The Earth pulls away from the sun while the sun pulls the Earth towards it. And therefore, we have a fixed location or orbit around the sun. So everything, moons, stars, planets, asteroids, everything has a pull on the other objects, right? The mass of the object, the distance of the object is going to affect that universal gravity. So universal gravity is the idea that if Venus is closer to the sun than Earth is, there's a greater gravitational pull from the sun happening on Venus compared to the Earth. When I look at the idea of mass, then, if I look at, well, I have the moon and I have the Earth close together, because the Earth is so much bigger than the moon, there is more gravitational pull on the Earth than there is on the moon. Right? So distance and mass are going to affect how universal gravitation happens. It also has to deal with the idea that when I have a size of an object spinning at approximately the same rate in its rotation, then we're going to increase our gravity as well. So you and I have a specific mass to me, right? I don't change if I travel out into space, but my weight, my measurement of gravitational pull definitely changes, right? So let's say I was 5'10" and 200 pounds. I wish, but I'm not, right? Then on Earth, I know how much I'm going to weigh. When I go to the moon as an astronaut, have I shrunk? Did I change my size? No, I'm still 5'10". But on the moon, because it's a much smaller object and it spins slower in its rotation, then I only weigh 33 pounds. Right? So there's a huge difference when it comes to the size of an object and how it affects the gravitational pull on the same object. The mass will stay the same. However, the weight, the measurement of gravitational pull, is going to change. All right, so tomorrow I'm going to give you the entire class to do your assignment. You should have plenty of time to get it done, but I would like you to have things with you in order to study once your assignment is finished. And if you need to make corrections on Chapter 2, Lesson 1, please do so you can get some points back.